Hi, today we're going to look at angle measures and segment lengths. And these angles and segments are all created by chords and secants and tangents within a circle. Let's look what happens. All right, so there's a couple theorems that we're going to work with first. This first one, this is a measure of an angle formed by two lines that intersect inside of a circle is half the sum of the measures of the intercepted arcs. Okay, that's kind of wordy, but here's the gist of it. If you get these two lines that intersect, and this is not necessarily the center of the circle. In fact, it's probably purposefully not the center of the circle. But what this says is that this angle 1, which happens to be a vertical angle, so it's also this angle here. Both of these are the same. But this angle is actually equal to half of these two intercepted arcs, this x and y that I have. Those two added up. So if I add those, take half of it, there's the angle measure right there. Okay, here's another one. What if instead of those chords or secants being intersecting inside the circle, what if they intersect outside the circle? Okay, so then they intersect out here, creating this angle 1. It's kind of the same idea. It creates these two arcs in between your secants, this arc x and arc y. And that measure of angle 1 is going to be half the difference of the two arcs. Rather than the sum, you're going to find the difference of them. So you either add your arcs or subtract your arcs, take half of it. Now, you do always want to take this bigger arc and subtract the smaller arc. Now, I drew this with, or the picture shows two secants. It also works with tangents. So if this is a secant and there's a tangent, it still creates these two arcs. So the rule here still applies. Or even if it's two tangents, it definitely can still create two arcs. Now, what's interesting about this picture, though, is that the two arcs created ultimately form the entire circle. So there's no like dead space of arc, like over here where you have this piece that you're not using at all. In this particular picture, you're going to use the whole 360 degrees of the circle. Okay, so let's practice this a little bit. Here we have them intersecting on the inside. So on the inside means I have to add the arcs. And the angle equals, so in this case, x equals 1/2 the sum of the arcs. So 46 plus 90. All right, and you can have your calculator handy. That's going to end up half of 136, which ends up equaling 68. Now that is an angle measurement, so I'll put a little degrees. Now here in picture B, this is the other scenario. This is where they intersect on the outside. So this angle is half the difference of these two. Now, this time they're switching it up on us. We're not looking for the angle. They actually told us the angle. I'm still going to set up a nice formula though. The angle is equal to half the difference of the arcs. Remember, take your big arc minus your small arc. All right, now, there's a couple ways that you can deal with this 1/2. You can try to distribute it, but it's not going to, half of 95 is not going to be very pretty. So another option, and you can do either way, it doesn't matter, but you could instead take and multiply both sides by 2/1. That way, that can get rid of the 1/2. And 2 times 20 is 40. Okay, then we would subtract the 95. That gets me -55 equals -z. So z would be 55 for that arc. Okay, what do you think? How about you try these three on your own to see if you can use those formulas to figure out. And remember, sometimes you add the arcs, sometimes you subtract the arcs. You try it, pause the video, come back when you're done. All right, here's what I have for answers. So check your 3 answers with mine. Go back and look through it if you missed them. Otherwise, let's keep moving. Okay, so this one's kind of like an application problem, a little trickier one. It says a satellite is a geostationary orbit, is in a, Let's try that again. A satellite in a geostationary orbit above Earth's equator has a viewing angle of Earth formed by two tangents. So you can see the picture here that the viewing angle is a 17.5 degree. The question is, what's the measure of the arc of Earth that is viewed from the satellite? So it can see this much of the Earth. This is the arc that we're looking for. All right, how about if we call that X? But here's the thing with this one. What's tricky about this is they didn't give you any information about the arc over here. But remember what I said about the two tangents? That ultimately this encompasses the entire circle. This is one arc and this is the rest of the 360 degrees. So what I would probably do is I'd go ahead, if the arc I'm looking for is X, then I'm going to call the other arc over here 360 minus X. Does that make sense? Because if we find out that like this is 60, well, since we know it's 360 all the way around, this would just be 360 minus, 60 or whatever this is. That's what we would call that. All right, so I'm going to use those measurements to go ahead and set up my formula then. And I'm going to say that the angle, which is 17.5, is equal to 1/2 the bigger arc, which is 360 minus X, minus the small arc. So it looks like that. And then just like on all the others, I'm going to multiply it by 2/1. And I end up with a 35 equals, and this would end up being 360 minus 2x. Okay, remember the halves went away, that's where that went. And then I'm going to subtract 360. And I get a negative 325 equals a negative 2x divided by negative 2. And the negatives will end up going away, and x equals 162.5. So that's how much of the Earth it sees. It kind of almost looks like it's half of it, but it's not quite half. 180 would be half. It sees 162.5 degrees of the Earth. All right, let's move on then. That's angles and arcs. Let's change it and let's look at some segment lengths and see what relationships we have on those. Let's start with our theorems. We have this scenario here, which looks familiar. See how there's the center? And these two chords are intersecting inside the circle somewhere. And we're purposefully, again, not making it be the center because it's not about the center at all. It's just two random chords. And it splits these chords up into sections. And you can see there's 4 separate sections. We call it A, B, C, and D. Well, when this happens, this is the relationship that will occur. If you take your A times your B, it will always equal your C times your D. All right, that's interesting. Handy, easy little relationship to deal with. Now, it gets a little trickier when they start to intersect on the exterior. It might be tempting to think it's the same idea where you take this segment times this segment equals this times this, but it's not that. Let's look at how this is set up. It's W plus X. So what that means is the entire segment times just the exterior part. Now look here. The entire segment, Y plus Z, that whole length, times just the exterior. So let's write that in here. This is kind of fancy. Let's just write words to help us. It's going to be the entire segment times the exterior segment. That's what we're multiplying. And each set would be equal to it. All right, if it happens that one of your secants actually ends up being a tangent, like this one is, well, we're still going to do the entire segment times the exterior. But since on the tangent, the entire segment is the exterior, you think of it, well, the entire is t and the exterior is t. So it's t times t, or in this case, t squared then. If it's a tangent, you can just square it. Let's practice using those theorems. All right, I'm going to start with this one where it's on the exterior. So remember what we're going to do. We're going to say that the exterior the entire times the exterior equals the entire times the exterior. Let's set this up. the entire, which is 6 plus 8, so that's 14, times the exterior, 6, equals the entire, this one I'm going to have to call it 7 plus y, times the exterior, times 7. And then we're just going to do some algebra and solve that for y. 14 times 6 is 84. Distribute the 7 would be a 49 plus 7y minus your 49. That ends up being 35. So y will be 5 units long. Okay, let's look at the next one. Same idea. It's still on the it's intersecting out here on the outside of it. So we do the entire times the exterior. So 16 and 8 is a 24. That's the entire. The exterior is 8. Equals, and then the other side happens to be a tangent. So the entire is really the same thing as the exterior. So it's z times z, or z squared. All right, 24 times 8 is, let me get my calculator going here, 24 times 8 gets me 192, and then what I have to do is I have to square root that. So I'm going to square root 192, and I get z to equal 13 point, I'll go one decimal place, it'll be 13.9 is the length of z. Okay, so these are yours to practice. I have one that's on the exterior and one that's on the interior. Remember that on the interior version, it's these two segments multiplied equal these two segments multiplied. All right, go ahead and pause the video, work through these two on your own, come back when you're done. All right, here's what I've got. They said round to the nearest tenth, so I ended up with a 13.8 and a 3.2. I did feel like this was a little bit confusing here, so you might have to, because I started off and I did 6.5 times 3, but after looking at this a little more closely, this is the 3, this is the m here. So you do the same segments multiplied, so it'd be a 6.5 times an m equals a 3 times a 7. All right, let's keep going. Now, this says go ahead and see what you can do. If you want to go ahead and try these on your own, go for it. Pause the video, go work through them. You can come back. Otherwise, I'm going to go ahead and get started and go through them. There's a lot of stuff going on here, so let's do a little bit at a time here. Starting with this one, I guess this angle here is 50. And I'm going to totally ignore this tangent. I guess I'm going to work on finding x. So this is intersecting on the exterior. So remember with the arcs that if you take the difference of these arcs and take half of it, that should get you your angle. So that would be the formula that I would do. I'd say 50 is equal to 1/2. Let me clean that up. 1/2 the difference of the arcs, which is 160 minus x. Always the big one minus the small one. And again, you have options on what you want to do with that 1/2. It wouldn't be bad to distribute it, but I've been in the habit of multiplying by 2/1 to get rid of it, so I'm going to continue with that. I get a 100 equals 160 minus x. When you subtract your 160, you get negative 60 equals negative x. So x is 60. Okay, so that's the first part. Now I'm going to work on y. This one's a little weird. We haven't really done one like this, but this actually still works. If I'm looking for this angle is an inscribed angle, and it's going to be half the intercepted arc. All right, so that was something from this y here, this angle is half of that arc. So if that arc, well, I haven't really found that arc yet, have I? But I could get there. If I now know that this is 60 and this is 160, together that's 210. No, it's not. It's 220. 220. What does that leave me for the rest of this? Well, I would just do 360 minus 220, which gets me 140. And if y, okay, so that's 140, that's the arc, and y is half the intercepted arc. So half of 140. Y would have to be 70. Okay, let's go over to this next picture. I've got x is this interior angle here, and remember, when it's on the inside here, I have to look at what my intercepted arcs are, and that's a little bit tricky on this one because I don't have any information on that, which would be part of it, and then I don't have any information on that, which is the other part. I could probably get there, but hey, let's try something different here. Because they handed me this nice 60 and 70, let's work with that, and let's find this angle instead. Because x is just a linear pair with that angle, so I could figure it out. I'm going to work on finding this. Let's call it z. So I know that that angle is equal to 1/2 the sum of those intercepted arcs. So that's half of 130. So z would equal 65. But that's not really what they want. Remember that when you have these intersecting, or these two angles that form a straight line, that's just supplementary. So if this one is 65, this is just 180 minus 65. That ends up getting me x to equal 115. Okay, so a little bit more challenging now. You got to kind of work around and find everything you can. Let's see what y is doing here. Working on y. Looks like this arc here is what y is, and I'm going to be using my 53, and it's intercepting this arc y, but then it's also intersecting, if you follow those lines, it's intersecting this right here. All right, so I'm going to have to find some additional information here to figure out what my y is going to be. There's a couple ways to do this, but I think probably the simplest is if you would notice here that this goes through the center of the circle. Right here's the center. So this is a diameter right here. And if that's a diameter, then this has to add up to 180 here. And so far, we've got a 60 and we've got a 70. What's left over here for this chunk? That's 130, so it would be 50. So now I know that that little piece is 50. Okay, I don't even know that I necessarily had to do that. I just needed to know that this whole arc over here is 180 degrees, because that's the one I want to match it up with the y here. So the angle is half the difference of these two arcs. So the angle, which is 53, is 1/2 the difference of those intercepted arcs. The big arc I already said was 180. Subtract the little arc, which I don't know that I'm searching for, that's my y. Let's get rid of our 1/2, multiply both sides by 2. 2 times 53 is a 106, equals 180 minus y. Subtract your 180. You're left with a negative 74, equals a negative y, so y is 74. So definitely getting into some more challenging problems here. You got to use all the different stuff that you've learned and apply it. Now the previous slide was working with arcs. This one is, and angles. This one is dealing more with those segment lengths. So it's those new rules for the segment lengths. Kind of keep those handy. What I have here, let's see if I work with the x. X is coming out here and it's intersecting on the exterior. Now there's a couple ways I could look at it. I could look at it with this segment, which I think I want to do because I know everything about this segment, rather than using the y over here because I don't know that yet. So I'm going to work on this right here. That. And so this is the whole x, or because it's intersecting on the exterior, you do the entire times the exterior equals entire times exterior. So starting with, let's do the one we know the numbers on. The entire, that's 22 times the exterior, 7. 22 times 7 equals, now let's do it with that segment that the x is on. The entire segment is the x plus the 5, and the exterior part of that is just 5. Okay, so this should look familiar. We've done this a bunch of times. You're going to distribute here. Go ahead and multiply your 22 times your 7. And that's going to get me 154 equals 5x plus 25. Subtract the 25. Okay, divide it by 5 and grab my calculator here, 129, and divide it by 5. And x is equal to 25.8. Okay, I should have written smaller there, sorry. I'm going to run out of room on this, I'm guessing. Okay, now I'm going to do the same thing, but I'm going to do it with the y. I'm going to look at the tangent here, that is y, and I'm going to stick with the segment here that I knew everything about, because it's going to still be the entire times the exterior equals, and then remember on the tangent, you just take the y times the y, or y squared. So I know that this is 154, and I'm just going to have to square root that. And I get 12.4 for my y value. All right, let's go to the next picture. Again, working with segments, but these are on the interior. So these were the ones, oh wait, I guess there's a little bit that's on the exterior. All right. Let's work on x first. This is kind of weird because there's like this little piece is x, this little piece is y, this little piece is 5, we got a 9. Out here, that's 7, and there's an 11. Okay, let's do this one right here. Got the 11, that's the tangent, so I'm going to do 11 squared equals, and then I'm going to work with this here, which I'm going to do the entire thing, which is actually cut up into 3 parts. It's the 5, it's the x, and the 7. So if I add all of those up to get the entire, that would be 12 plus x. And then just the exterior part of that is 7. And then that equals, on my tangent, 11 squared. So distribute your 7. Subtract your 84. That's 37, divide by 7. So 37 divided by 7 gets me gets me 5.3. Okay, got it. Yep, totally ran out of room. Think I can squeeze this last part in? Okie doke. We have y, which is this little segment here. And on this one, I think what I'm going to do is I'm going to be using the 2 chords intersecting on the interior, and ignore this 7 and 11. That's not part of it. I'm going to stop it right here, and I'm going to say x times 5 equals y times 9. But I happen to know what x is now, so I'm not going to really say x. I'm going to say 5.3. So 5.3 times 5, I'm going to squeeze it in right here. 5.3 times 5 equals, going the other direction, y times 9. So 5.3 times 5 is 26.5 equals 9y. Now just divide by 9. And I get y to equal 2.9. Okay, I think these are kind of fun. It's kind of challenging, but you got to think through all the different things that we learned and try to use all of it together. All right, hope this helps. Good luck.